Hey everybody, this is Mr. Drogemeyer. Thanks for joining me for our Algebra 1A Unit 4 test review. Today we're going to work through several different problem examples that will be very similar to what you will see when you take that Unit 4 test. So let's go ahead and we'll jump right in with our first question here. And in this one, they want us to match the equation and its input-output table with the graph. And so what we want to look for here, we have our x values in the table, we have our y values, we also have the equation given. But so any pair here of x and y values, I should be able then to plot that on that graph. So for example, in both cases, it says that when x is 0, y is 2. And so if you look at these graphs, when x is 0, or excuse me, when x is 0, y is 2, x is 0, y is 2. Let's look at this first table. When x is negative 2, it says that y is positive 6. Well, here, when x is negative 2, my y value is actually down here in the negatives at negative 2. So that tells me this table is going to go with that graph, and the first table is going to go with this second graph, because when x is negative 2 on this one, our y value is up here at 6. So just looking at those table values and working to plot those points to check those graphs. So for number 2, it says a researcher developed a linear model for a sensor based on 2 readings. Later, the researcher discovers there was a bias error, and so the y values for both readings were too high by a fixed amount. So how will our corrected model differ from the original model? So it's a linear model, means that it's going to be a line. I'm going to just create just a sample thing of data here. So let's say we had 2 readings. Let's say when x was 1, y was 10. When x was 2, y was 15. And they said that these were too high by a fixed amount. So meaning that when they rerun the model and it corrects, those y values are going to come down by the same amount. So let's say that when they rerun it, when x is 1, y is 5. When x is 2, y is 10. So if we're thinking in terms of linear, a line has a slope and it has a y-intercept. Well, we could find our slopes here. So we talked about finding slope. We take the difference between the y values over the difference between the x values. And so that's a slope of 5 here. 15 minus 10 is 5. 2 minus 1 is 1. Do the same thing here. Difference between your y values, difference between your x values, still 5 over 1. So our slope isn't going to change with the corrected model. Let's think about a y-intercept. So that's where the graph crosses the y-axis. So when x is 0, well, we didn't put an example in here for 0, but a line has the same slope at every point. And so if our slope was 5, when we go down to 0, this would go down to 5. This one would go down to 0. That y-intercept is going to change. And so, and it will actually, it would actually move down because of that. So just trying to interpret what happens with a graph. All right, let's take a look at number 3. So in this one, it says Eric claims that these 3 equations here, y squared equals 4x plus 4, y to the third equals 4x plus 4, and y equals x to the third plus 4 are all functions. And we want to know, is he correct? And if not, what's his mistake? And which ones really are functions? So for this one, I would go ahead and use my Desmos calculator, because that way I can see it on the graph. I can use my vertical line test. So I've already put these into into Desmo. So here's the first one, y squared equals 4x plus 4. And notice here, if we think of our vertical line test, when I run a vertical line um, across here, and let's just do that, that will give you that visual. And so if we slide that across, you'll notice it's hitting two different points pretty much everywhere on there. And to be a function, the vertical line test says that we're only going to touch one point on that function. So this first one, that's not going to be a function. If we look at our second graph here, y to the third equals 4x plus 4. And again, I'm going to use the slider here with our vertical line test. We're always hitting one point here, one point. It's getting a little tough to tell there, but we're never actually hitting two different points on that graph. It looks like it could happen here, but this is getting closer and closer. If we zoomed in that whole time, it's getting closer and closer to that -1, and then it flips over. So this one does look like it is a function. And then our last one, y equals x to the third plus 4. And so again, only hitting one point everywhere we go all the way through. So that one is also a function. So when we go back to our question here, he is not correct. This first one is a function, or excuse me, is not a function, we said. The other two, they are functions. So they passed that vertical line test. The first one did not. All right, then number 4. Here we have 4 different graphs, and they want us to find the domain of each graph. And so with each of these, so domain is our x values. With each of these, they're starting at 0 and going to an x value of 4. But you'll notice sometimes we have a closed circle, sometimes we have the open circle. So anytime we have the closed circle, that means that it can be equal to 0. When we have the open circle, that means it can't be equal to that number. It can't be equal to 4. So our domain for this first graph, x is going to be greater than or equal to 0, and it's going to be less than 4. It can't equal 4. For our second one here, we have closed circles at both points. And so we would say the domain for that one would be x is greater than or equal to 0, x is less than or equal to 4. In our third graph, open circle at 0, so it can't equal 0. Closed circle at 4, it can equal 4. So x is greater than 0, and it's less than or equal to 4. And then our last one here, we have open circles at both 0 and 4. And so that means x is greater than 0, but less than 4. All right, moving on then to number 5. Here we want to write a function that models this description. So it says a woman ran a total of 12 miles over a 2-hour period. And so all they're asking us to do here is we want to recognize what's our input, what's our output. Well, the 2 hours would be our input. The 12 miles would be our output. So for our function, when our input is 2, f of 2 is going to equal 12. So that's what we're looking for in that one, just identifying what that would look like. All right, on to number 6. And in this one, we're dealing with some recursive formulas, and we're writing recursive formulas for these sequences. So to write the recursive formula, we always start by noting what f of 1 is. So what's our first value in our sequence? So here we say f of 1 is 5. And then to write our formula for f of n, we're going to start with f of n minus 1. So that's going to be the term in the sequence that comes before the term we're looking at. And then we want to look at how is it our sequence changing each time. Well, you'll notice each time we go to the next term, we're adding 2. So this is going to be plus 2. And we need to note that this is for cases when n is greater than 1. So for example, if I want to find f of 2, I start with the value for f of 1, which is 5, and add 2. F of 2 is going to be 7. We could also find the explicit formula for this. To find the explicit formula, we take the starting value, which in this case was 5. We add that common difference that's going in between each term. So each time we're increasing by 2, and then we multiply that by n minus 1. And so this is our explicit formula. And sorry about that. This one is our recursive formula. And we could go ahead and simplify this explicit one by distributing the 2. I'm just going to do that real quick to show you what that looks like. So 2 times n is 2n, 2 times -1 is -2, and then we combine like terms. So the simplified form of this explicit formula would be 2n, and we have 5 minus 2, which would be a positive 3. So recursive formula here, and in our simplified form of the explicit formula is 2n plus 3. All right, and then let's do this last one here. We'll just do the recursive on this one since that's what they asked us for. So f of 1, our first term is 2. To find our recursive formula for f of n, we're going to take that previous value, f of n minus 1, and in this case, our common difference, or how it's changing each time, it's decreasing by 1. So this would be our recursive formula for this one. F of n is going to be equal to f of n minus 1 for n values that are greater than 1. All right, then moving on to number 7. Here we want to write a function that's described by this recursive notation. So we're going to go from recursive to an explicit function. So f of 1 is 7, f of n minus 1 plus 3 for n values that are greater than 1. So we said that plus 3 at the end, that is what we call our common difference in our sequence. So to write an explicit formula, we need to know that common difference, and then we need to know what's our initial value. What do we have for f of 1? Once we have that, then we can write our function. It's always going to be the initial value plus the common difference times n minus 1. And now we can go ahead and simplify again like we just did with the one on the last slide. I'm going to distribute that 3. So we get 7 plus 3 times n is 3n. 3 times -1 is -3. And now we want to combine our like terms. 7 minus 3 is 4. So it's going to be 3n plus 4 is going to be our formula. All right, number 8 is talking about rate of change. And when we talked about rate of change, we said that we take f of a minus f of b over a minus b. And so if we look at the terms we have here, we just need to call one of the, or think of one of these as a and one of these as b. So my f of a value, which is going to be my outputs that are up top here, I'm just going to go in order that they gave me. I'm going to take the 317 minus the 296. Those are my outputs. My inputs are 2 and 5. So I'm subtracting outputs, subtracting inputs. 317 minus 296. When I subtract that, I get 21. 2 minus 5 is negative 3. So my rate of change is going to be 21 over negative 3. If I simplify that, 21 divided by negative 3 is going to be negative 7. So negative 7 would be our rate of change for that one. All right, moving on then to number 9. All right, this one, again, we're doing some rates of change here. It says we have 4 different towns in the same state. They grew in size. And then they give us population of town A, how it changed, B, C, and D. We want to know which town had the least average change in population over the time period that they gave us. So we're going to calculate the rate of change for each of these. So we got A, B, C, and D, and then we want to see which one has the lowest average change. So for A, population went from 20,000 to 24,500. So I'm going to subtract those. So 24,500 minus 20,000. And then 3 years. Well, that's 4,500 when I do that subtraction over 3. And when you do that division, 4,500 divided by 3, it increased by an average of 1,500 people per year. Letter B, I have 34,770 and 30,200. When I subtract those, I get 4,570. That was over a 5-year period. And then do the division, 4,570 divided by 5. That one comes to 914 people each year. Letter C, 22,000 minus 17,000 is 5,000. This one was over 4 years. 5,000 divided by 4 is 1,250 people per year. And then the last one, 34,100 minus 30,000 is 4,100. This was over a 2-year period. And so 4,100 divided by 2 is 2,050. So our least average change is going to be letter B, the 914 people every year on average. All right, on to number 10. This time we have 2 tables. They've asked us to find the average rate of change over the interval from 0 to 3. So when we're talking about the interval, that's talking about the x values. So from 0 to 3, rate of change, we're going to take the y value at 3 minus the y value at 0, divide it by the x value at 3, x value at 0. So that's 9 over 3. The rate of change for this one is going to be 3, positive 3. For our second table, so again, going from 0 to 3, y value at 3 is 30, y value at 0 is 5. The x value at 3 is 3, x value at 0 is 0. 30 minus 5 is 25, 3 minus 0 is 3. So we get 25 thirds. If we do that as a mixed number, that would be 8 and 1/3. 23 goes into 25 8 times. We'd have 1 left over. So 8 and 1/3 would be the average rate of change for that one. All right, number 11, same type of problem here. This time we're going from 1 to 4, and they want to know which of these tables would have the greatest rate of change over that interval. All right, so again, y value or f of x value at 4 minus the y value at 1 would be 24. And then x value of 4, x value of 1, we're going to do those subtractions. 60 minus 24 is 36. 4 minus 1 is 3. And 36 divided by 3 is 12. So this is our rate of change for that one. In our second one here, The y value at 4 is 45. The y value at 1 is 10. And then 4 minus 1 are x values. 45 minus 10 is 35. 4 minus 1 is 3. This is going to be 35 thirds, or as a mixed number, that would be 11 and 2/3. And so greatest rate of change over that interval was the first table with a rate of change of 12. All right, we're hitting the back stretch here. Let's move on to number 12. All right, again, asking us to do a recursive formula. And so with this one, we find that first value in the sequence, f of 1, is 4. Once we have that, we're going to find our f of n, which is going to be equal to f of n minus 1, the previous value in the sequence. And this time, our common difference is 8, so we're going to add 8 each time. And this is, again, for any n values greater than 1. So that would be our recursive formula for that sequence. In number 13, we want to write an explicit function, explicit formula for that sequence. With these, we said we're going to find f of n by finding the initial value in the sequence, which is -3. And then to that, we're going to add what's our common difference. Well, if you'll notice here, each time the next term increases by 5. So we take that times the n minus 1. So this is how we set up our explicit function. And now to simplify it, we can distribute that 5 to each term inside the parentheses. So that would be 5 times n is 5n. 5 times -1 is -5. Combine our like terms. -3 minus 5 is -8. So this is going to be 5n minus 8 would be our explicit formula or explicit function for that sequence. You can always check this as well. So just as an example, our third term in our sequence is 7. So if I plug in 3 for n, so f of 3, if this is correct, should equal 7. Well, 5 times 3 minus 8, 5 times 3 is 15. 15 minus 8, that does equal 7. So just a way that you can check your function after you've set it up as well. All right, on to number 14. We want to give an example of a relation in real life and explain why it is a function. All right, so this is an essay type of question here. What we would want to talk about is what makes something a function. Well, when we talked about functions, we talked about we have inputs and outputs. To be a function, each input has only one output. So that's probably the most important part of this explanation. And then we just want to come up with a real life example. So one that I can think of is if I take a car trip. So I take a trip in my car. I could explain a function in terms of my my hours and miles. So hours would be my input, miles would be my output. So that's just a simple example, real life example of something that could be explained by a function. All right, on to 15. And in this one, it says we have a graph with a domain that they've given there. First, we want to describe the endpoints of the graph. Well, if this is our domain, then that means that when x equals 3, that's going to be the left endpoint. And when x equals 7, that's going to be the right endpoint. So that's where the endpoints are. What would those look like on the graph? Well, since we just have x is greater than 3, it can't be equal to 3, we would have an open circle for the left endpoint. And since x can equal 7, we would have a closed or a filled circle for the right end. All right, and then they also ask what if the corresponding y values for those endpoints would be included in the range of the function. Well, and so what that means is since x can't equal 3 because of our domain, then that means that the y value at x equals 3, that's going to be an open circle. And so we would say the y value of the left end is not included in the range of the function because of that open circle. On the right side, that one's a closed circle, so that point is a part of the function. So the y value of the right end is included in the range. All right, so hopefully that makes sense with that question. We've got two more here before we wrap up. Number 16, they've given us a function f of 4 equals 48. Their statement, they just want us to come up with an interpretation of that. So basically what they're saying is, what's a situation that you could apply to that f of 4 equals 48? Well, so we know that the input is 4 and the output is 48. And so just one example that I could think of is I could say something like, Jake bought 4 t-shirts and paid a total of $48. And so if the t-shirts were $12 a piece, he's buying 4 of them. 4 is our input. So when he buys 4, the cost is $48. So there's just a way that you can apply that statement or give an interpretation that would apply to it. All right, and then finally, number 17 says, in your own words, explain how to find the rate of change of the following graph at x equals 2, and then find the rate of change at x equals 2. All right, so x equals 2, the point on that graph is right there. If we want to find the rate of change at that point, we want to pick 2 points on the graph that are on either side of that point. So I'm going to pick these two. So I'm going to pick the points 0, 4 and 4, 2. So we want to pick 2 points on either side of that x equals 2. Once we have those points, now we can use our rate of change formula that we had. So if I take the y value from one point minus the y value from the other, then take the x value from that first point minus the x value from the second point. Now I just need to do that math. 4 minus 2 is 2. 0 minus 4 is negative 4. And so we would have an average rate of change at x equals 2 of 2 over negative 4. Well, if I simplify that, they're both divisible by 2. One's positive, one's negative. We would say that our rate of change for this, or at x equals 2, is negative 1/2. So that's how we can take a graph and find that rate of change. All right, and that's all I've got for you. I appreciate you taking the time to watch the video. And as always, if you do have questions, please let me know. Thanks. Have a great day.